Hi, and welcome back to my channel. So in this video I want to start exploring amplification setups for the HackRF. So as you know for sure, the HackRF has a quite limited transmit output. Nominally can achieve around 10 or 15 dBm, but on many frequencies in fact it can barely reach 0 dBm. Okay, so in fact if you have a look at my episode 37, you can see a bunch of configurations. For example, as you can see here, we are at about 440 megahertz, and with the settings here we have basically almost max settings. We can only output around 0 dBm. So if you're interested in that experiment, just look at episode 37. So of course the idea is to amplify the signal with some kind of amplifier. So this keeps moving. So I decided to buy a cheap one to start my experiments, and the one I went for is of course from China, and it is this one. Right, so yes, so as you can see, it's this amplifier. It costs around $11.50, so relatively cheap, and it works here. It says from 2 megahertz to 700 megahertz, and it can deliver let's see how much, around 35 dBm. Okay, so that's about 3 watts of power, and it requires a DC source of between 12 and 15 volts, which is good because it can be powered by a LiPo battery, for example. That's a good DC value. And so yeah, in my video I'm going to experiment with it. Okay, so keep in mind that I had to solder these leads for the power. These are not provided with the unit I bought, but okay, it's just a simple soldering task. It takes a second, and then you have these things. So in order to test this unit, of course I cannot connect something with 1 watt or even more of power to the spectrum analyzer directly. So I'm going to use this attenuator that I just received. It's a nice, as you can see, Narda 776B30 attenuator, and as you can see, it's rated up to 50 watts, and it works in theory well from DC to 18 gigahertz, which is quite a lot. And so the idea is that I'm going to chain things this way. The HackRF is going to produce a signal which is going to the amplifier, which is then going to this attenuator, and then we will measure the result with the spectrum analyzer. So this is the setup, and so let me start preparing it for the rest of this video. Okay, so before starting to experiment with the HackRF and the amplifier, I want to make sure that this attenuator works well. By the way, if you're curious, I already showed you the model number, but here are the details of this attenuator. So yeah, it's rated 50 watts. This is the model I have. It's rated 50 watts, but it can handle also a peak of 1 kilowatts, which is extremely good. So I feel very safe with this. Okay, yeah, so in order to verify it, let me use the spectrum analyzer. So here it is, and so at the moment we are looking at the spectrum from 0 to 1.8 gigahertz. So in fact, let me start from just 1 megahertz. That's better for the tracking generator. And the idea is that I'm going to emit a signal from here, the tracking generator. The signal is going to the attenuator, it's coming back to here, and it's going inside the spectrum analyzer. So let's see what happens. Ideally, we would like to see a flat line at so the tracking generator here is going to emit a signal, as you can see, of you can see even here, of minus 10 dBm. And so I expect a flat line of at minus 40 dBm. Let's see what happens. Start, and there it is. Okay, fantastic. We have our flat line at minus 40 dBm, and if I play with the power here of the tracking generator, yeah, the line stays flat when I move things up and the source power up and down. Okay, so this attenuator is indeed working as expected. It's a good attenuator, at least up to 1.8 gigahertz. This is rated 18 gigahertz, but I cannot test this at the moment. Okay, so in fact I want to attenuate this even more, and I'm going to use this other attenuator that I have. It's a cheap 30 dB attenuator from China that I used in many of my videos. I don't know if we can focus this thing. Anyway, this cost about a couple of euros. And so let me stop the tracking generator. Okay, and let me inline this other attenuator here. Okay, so we can see what happens. Okay, it's a bit okay, so I have probably to unplug this. Yeah, there is a bit of tension on these connectors, which is not great, but okay, so let me inline. Here I'm also using just it's not really necessary, but I'm also using a DC blocker because later on we will connect the HackRF, so I want to make sure that no DC is going into the spectrum analyzer. Even though this spectrum analyzer can handle up to 25 volts, so that should be no problem really, but just to be completely safe. Okay, so okay, right. So now I have chained this attenuator and this other attenuator. So I expect a total of 60 dB of attenuation. So let me. At the moment, the noise floor, as you can see, is here it's a minus 67 or something, okay? So I'm now going to produce a signal at 0 dBm, so I expect a flat line at around minus 60. So let's see if that works fine. Source 0 dBm, right? And so here we get our line at minus 60 as expected. It says minus 58, I guess. Yeah, let me actually use some averaging so we can be more precise. And that's right. Now we see that it is actually minus 61 something. And the extra one could be for a lot of reasons, including losses in the cable or the connectors and these kind of things. Anyway, this is a perfect, the perfect response that I was expecting. There is an interesting feature that is present in most spectrum analyzers, but I never used it in my previous videos. But here I can set an external preamp value. In this case, the preamp is actually an attenuator, so I'm going to write minus 60 dB, minus 60. And so the spectrum analyzer is automatically compensating for the minus 60 attenuation that we have. So as you can see here, it's showing that the tracking generator here is actually emitting something at around minus 1 or minus 60. Okay, so now I can basically move my reference much lower, and right. And so we will be able to see now that we connect the HackRF, the amplifier, the signal here automatically calculated. So we will be able to measure without doing any minus 60 calculations on the fly. We will see what is the power emitted by the HackRF with the amplifier. So let me now do that. Okay, so I have completed the setup now. I have my HackRF with the PortaPack extension. It's running the new Mayhem Havoc firmware. So just have a look at my previous episode if you want to know more about this new firmware for the PortaPack. The output of the HackRF is going to the amplifier here. It has a port called RF in. Okay, so that's where your HackRF input should go. The output is going to the attenuator, which is then going to this other attenuator and also DC blocker, just to be safe. And then this goes directly to the spectrum analyzer. Here I have connected the power cable of the amplifier to this, as you can see here, sorry, to this power supply here. At the moment it's set at 12 volts and with a limit of about 600 milliamps. Okay, so it's not running yet, but let me activate it. Okay, so it's running now. So the amplifier is consuming power, and as you can see, it's only consuming 530 milliampere at this voltage. Okay, and just out of curiosity, if I increase the voltage a little bit, as you can see, the amperage is not increasing so much. So yeah, it doesn't really matter so much how much voltage you give. Above 12 is completely fine. So right. Anyway, let's now focus on the experiment. So you can see the spectrum analyzer here, and I'm now going to play with the signal generator functionality of the Portapack. Okay, so let me set up it just one sec. Okay, all right. So I'm going to use I'm going to start with the minimum value for the power. So 0 IF gain, but I'm going to use the 14 RF gain. Okay, and I'm going to start. Let's see, at let's say at around 440 megahertz. Okay, so that's UHF. Okay, UHF frequencies. So let me start and see what happens. Okay, so now the HackRF is emitting its power, and you can see here a peak around, where is it? I guess it's here. Yeah, that's our 440. Okay, so at the moment it says minus 5 more or less dBm, and so let's see what happens when I start increasing the output power of the HackRF. So at the moment, as I said, is 0 IF. Let me put it to 10. And so correspondingly, the output is going up. Let me go to 20 IF. And so now we are outputting this 10 dBm out, okay, which is good. So let me move on to 30 IF. And we have our 19 dBm of power out. And so far it's pretty clean, as you can see. Yeah, we have this amplification of this spurious emission of the HackRF, but they are still confined at around 0 dBm, so I guess it's kind of okay so far. Yeah, so let's go back to our main carrier here, and we are at 30 IF. Okay, so I'm now going to 35. And as you can see, around here we start seeing also the amplification. So the HackRF is starting producing also harmonics, and also these get amplified, of course. Let me reach 40, and we are getting on the main carrier 27 dBm. So that's about half a watt, okay? At half a watt, things are still more or less under control, in the sense that the first harmonics, well, no, unfortunately the first harmonic now is at 5 dBm. So at this level, I think you need to, filter the output already. So it's not acceptable to emit a spurious signal at 5 dBm in this frequency. Anyway, let's see, just out of curiosity, what is the maximum you can reach on the main carrier here. So we are at 28. 29. Now I'm 43 IF gain, and if I remember correctly, at this setting the HackRF is actually outputting 0 dBm, okay, on the carrier, and so here we are getting about 30 dB of amplification. And so let me go up and see. Now I'm 44, 45, 46, 47. So this is the maximum settings on the HackRF. And as you can see, we are getting about 30 dBm, which is 1 watt. Okay, so you can get basically with this at UHF frequencies, with this amplifier, you can get 1 watt of power out. But yeah, you will have to, definitely you will have to clean the signal with a filter. Okay, so let's see what happens, for example, at VHF frequencies, so 144 megahertz. And oh wow, okay, so let's see. Here we get our 32 dBm, so it's actually quite stronger on VHF, but you can see we get also a lot of harmonics. So let me see what happens if I reduce a little bit the power. So the harmonics here are generated by a combination of the harmonics, unfortunately generated by the HackRF, and also this distortion created by the amplifier. So together, as you can see, they produce quite a lot of harmonics. So let me reduce the level on the HackRF to 40 IF. So still we have quite a bit of harmonics. I'm now at 29 on the IF on the HackRF. And so yeah, basically we can get around 30 dBm, but again, it's absolutely necessary to filter things. Here at 15 dBm, so I have IF set to 15 on the HackRF, and I'm getting 15 dBs on the output. And there are basically no harmonics beside the ones on the lower frequencies. So yeah, I guess you can get 15 dBms is how much? Is about 300 milliwatts of power, I guess. No, sorry, 30 dB, 30 milliwatts. So yeah, it's not so much. Okay, so let's move on to much lower frequencies, so the HF frequencies. So let me stop frequency, let me put 100 megahertz. And I'm now going to emit a signal at, let's say, 7 megahertz. Okay, so this is our signal at 7 megahertz, as you can see, it's there. And at the moment I have an IF gain of only 15, but a lot of harmonics. So this amplifier is creating a lot of harmonics at low frequencies, unfortunately. Let me increase the gain anyway. Now I am at 30 IF. It's pretty horrible, yes. Yeah, and if I go up, now I'm at 40. As you can see, we are not increasing so much the power of the carrier, but just of the spurious emissions. So yeah, it's not so great. Let me see at what level the harmonics go down decently. Okay, now we are at IF gain of 4. Yeah, that's pretty bad. So again, we can get around 32 dB of power output, but the output definitely requires filtering. Okay, so I think basically the conclusion is that this amplifier works fine for amplifying, but creates a lot of harmonics. So you need amplification. You need amplifications. So let me see what happens, for example, at 14 megahertz, just to try another thing. And similar, as you can see, we have a lot of harmonics. The main carrier here is at 32 dBm, 33 almost, which is 2 watts, which is great, but you also have harmonics. So let me actually touch the amplifier here to oh, it's very warm. Oh, I cannot even keep my hand. So yeah, it's very warm. Yeah, it's very warm. So either you use it for a very low amount of time, or you add some kind of fan, I guess, or use a better dissipator there, because it's at this level of it's producing about 2 watts of output. It's very warm. Yeah, I mean, I can touch it. It's not impossible to touch it, but after, let's say, 5 seconds, I really want to take my hand away. So that's it for this video. This was a first experiment with this amplifier. And my conclusion, well, let's see if I can conclude somehow. Yeah, my conclusion is that now we are at IF equals 0 here. So I know that the HackRF is not producing many harmonics at this level. Yeah, by the way, no. Okay, these, as you can see, the harmonics start appearing at this point, this signal that we have here, which is present even at the lowest setting, is not harmonics, it's just noise generated by the HackRF, independently on the frequency of the main carrier. So for example, if I change the frequency, I don't know, to 10 megahertz, let's try to do that. Okay, so as you can see, now we have the main carrier at 10, but still we get this signal here. So this is noise generated by the HackRF, independent of the frequency, which gets amplified. And let me see, it gets amplified up to yeah, about 0 dBm. So yeah, my conclusion is that when using an amplifier like this, it's definitely necessary to do some filtering. Anyway, I hope you found this video interesting, and I'll see you next time. Bye bye.